Good day. Graham Hillestrand, CEO, Embedded Systems Technology. Welcome to part 3 of our 4-part series on model-based design of mobile cyber-physical systems, the conceiving and engineering of safe mobile systems and systems of systems. And once again, we're pleased to present our partners in this endeavor that make up our ecosystem, the MathWorks, Synopsys, SimuQuest, Mechanical Simulation Corporation, Invitech, and ACART, the Advanced Center for Automotive Research and Testing. What we'll cover in part 3 is the modeling and simulation of systems using the ESSE Workbench. You'll remember that we did cover the ESSE Workbench in terms of any model, any simulator, any tool. We talked in part 2 about modeling subsystems up to systems, and this time we'll talk about systems of systems, cooperating vehicles, with some limitations of mobile Wi-Fi and radar, and this will be original research from EST. We also looked at the instantaneous computation of fuel consumption and gas emissions in our last part 2 presentation, and just remember that as we're going through the video demonstrations for this. High fidelity modeling, high performance simulation of multiple communicating vehicles, radar and mobile Wi-Fi communication between vehicles, and developing software on ECUs using the ESSE Workbench and Synopsys ECU models. So here's our review. ESSE Workbench, any model, any simulator, any tool. We saw this both in part 1 and part 2. Multi-core simulator, multi-core modeling, system network fabric, which is the ESSE technology for building high-performance, bit-accurate, timing-accurate models of networks, CAN, FlexRay, mobile Wi-Fi, etc. The tools and models that are supported are mapped automatically or under user control to cores. A variety of models from discrete to continuous domain to vehicle dynamics models. Constituting all of the models that you'd require to build the real-time control system of a vehicle, and that would then simulate across multiple cores using multiple SNF networks which are connecting the models together. On Linux and Windows, any model, any simulator, any tool. Second, we looked at the ESSE Workbench, the full vehicle control system development, concurrent development, verification and proving. In that sense, we had a golden reference model which we developed in part 2. We showed how that would derive an operational system model where the operational systems would still have the continuous domain plant models, but their control would be now timing accurate ECU models running real software, or software in the loop type models connected by SE, SNF networks, CAN network here, FlexRay network there, for instance. In that sense, we have teams of engineers developing hardware and software, these operational models, comparing it in function and timing with the golden reference models, reporting aberrations, allowing these guys to fix it during the development cycle rather than later during the verification cycle. Also running debuggers on the ECUs to pick up software problems during development, being able to plug these into vehicle dynamics models, running common test data for both the vehicle dynamics model, including the golden reference, vehicle dynamics, including the operational models, and picking up visually differences in operation and performance. Highly stimulating to groups of engineers. But that's the summary of our ESSE Workbench. So let's move on to Success Report 2, Inter-Vehicle Cooperative Control for Active Safety. This is part of verification for full vehicles operating in traffic. So here is detection and communication technologies, and we're looking at those and measuring it with inter-vehicle cooperative control for active safety. So the objective here, identify the limits of communication detection technologies, that's radar, DSRC, and investigation of cooperative control strategies in traffic in order to, say, avoid collisions, improve safety margins, increase fuel efficiency, reduce emissions, and improve infrastructure utilization. We have selected empirical studies with some results from that, and we'll talk about those in a moment. So each of these vehicles will have an adaptive cruise controller, a GIPS following model. There's some limitations of that. The GIPS following model speeds up when radar doesn't detect a lead vehicle, slows down when it does, and it needs to match the speed of the vehicle ahead if it's following it. We looked at combinations of detection between fixed radar and dedicated short-range communication, and here are some results. Radar only is unsafe. When following vehicle loses the lead vehicle, then it tends to accelerate, and if it can't decelerate in time, collision results. V2V, surprisingly, is unsafe in congested traffic. It can't guarantee that messages will be received even from close vehicles. Something that's safer is vehicle-vehicle DSRC plus radar, and one of the better, or maybe even the best, is multiple DSRC V2V radios, possibly V2V infrastructure as well, so that maybe 2 or 3 radar radios, and steerable radar, and possibly other sensors. So let's see what we're going to look at in terms of our simulated system here. So we're going to look at 2 cars, one following car, one leading car, and we're going to look at the electronics in these cars, and we're going to see how they perform in terms of radar and DSRC. And remember, we saw exactly this configuration of vehicles for computing instantaneous and aggregate emissions of CO, CO2, and NO, and instantaneous consumption of fuel and aggregate consumption of fuel. So that's basically the environment that we're going to be playing in. Let me go back to our presentation now, and we'll move on. This is the experimental setup for our system. We'll have adaptive cruise control between 2 vehicles. We've actually run up to 6 in platoon mode here, but we'll look at 2 today. Each model has a transmission plant controlled by a controller, which is in this case the transmission by an Infineon tricore based ECU with a louted back debugger connected to it. The internal combustion engine will be a table lookup engine controlled by a software-in-the-loop controller. Body controller controlled by another Infineon tricore based ECU, and a second louder back debugger will be attached there. We have DSRC, that is IEEE 802.11p plus MAC, ESSE models, radar, which is another ESSE model controlled by an ECU, adaptive cruise control and driver model controlled by a shared ECU as well. Fast active CAN bus connecting the 2 tricores. We'll have a CAN monitor on that, and we'll look at the integrating this into 2 vehicle dynamics models, and we'll run these in a simulation which will have 2 vehicles. And these, of course, are communicating by both radar and DSRC. Okay, so the 2 vehicle simulation runs on 6 cores. The 6 runs on 24 cores with near real-time performance. So let's see what the architecture of this looks like. Here's our car sim model. We have an engine model, which is Simulink, controlled by a software-in-the-loop controller. Transmission model, again Simulink, controlled by software running on an Infineon tricore. This is real software. There's our mechanical connection. Body control, a VECU body controller running, again, software on an Infineon tricore, connected by a CAN network, a little CAN monitor sitting out there. We'll be interested in DSRC, and we'll be interested in radar. And we'll put together there a controller to control DSRC and radar, together with the driver model sitting in that driver's seat, presumably, and adaptive cruise control. Now, to make this interesting, we'll run another model which is exactly the same. So what we're going to show here is the characteristic performance of these vehicles in that 2-car simulation that we saw a video of before, and we're also going to look at software development using that system. So here we go. So I'm firing up Synopsys Comet system here. We're firing up the ESSE CAN monitor. We're firing up a Lauterbach debugger. And I'll just expose a little bit of this as we're doing that. We're watching this CAN bus transmit messages across here between these two controllers. So that's quite interesting. We're now using the Lauterbach debugger to look at the source code running on this controller. We'll have a quick look at some of the characteristics of the cars running together, and we're looking at gear changing here. We'll go to the second Lauterbach debugger. We're looking at the assembler code generated from the source. We're going to put some debug information in here as well. So we're now watching the Lauterbach debugger on this ECU. We've watched on that. We're watching CAN network traffic across here. And here we're watching underneath what's happening in the 6 cores of the 8 cores on this multi-core simulation system. Notice those 6 cores are very busy. So let's continue with this. We're back looking at the CAN network. I'll just skip along here a little bit. We put a breakpoint in at 40 seconds here. Notice that we're very busy. We've got all of these physical cores quite active. We're coming into the breakpoint. We've got a breakpoint. All the cores drop off, so they're now running. They've now stopped. And we'll go and see what's happening in the 2 cars. So the first is, here is the gear changing lead car, trailing car going through that sequence of start-stop. We'll move up and have a look at the longitudinal speed of each of these cars, leading, following car. This is the throttle control of the 2 vehicles. You'll notice it's not so steady. The PI controller is not so terrific here. We're looking at wheel spin here on the left and right wheels of the lead vehicle and the trailing vehicle. And finally, we're looking at the torque generated by the engine on the crankshaft, etc., etc. Okay, so let's go back to our presentation. So that's what we saw. We saw 2 vehicles. We saw this assembly. We saw software being developed on this, and we saw what was happening on the CAN bus and in the vehicle models. So a summary of what we did see in this part 3, the modeling of systems and systems with cooperating vehicles and some limitations of mobile Wi-Fi, and we announced there some original results from EST with respect to the safety or lack of safety of DSRC type communication. We looked at high fidelity modeling and high performance simulation of multiple communicating vehicles. Each of those vehicles was fitted with a radar model and a mobile Wi-Fi communication model between those 2 vehicles. We looked at the instantaneous computation of fuel consumption and gas emissions in part 2. When we combined that with the data we're getting from the vehicle dynamics models of having complex engine models, and these were ACART engine models we were using in this case, are controlled by timing accurate and functionally accurate VECU models running real software. And we looked at developing software and debugging that software on multiple ECUs in the ESSE Workbench. So that's the summary of part 3. Thank you very much for your attention, and we invite you back to part 4 at any time you'd like to look at it, and we'd welcome you there.